Here's an example. We can talk about the maximal elements, the greatest elements, etc. Here we have a poset um, given with the Hasse diagram. And of course, we see that A is a minimal element and H and I are maximal elements. This is clear. But for instance, A is the least element, but neither H nor I are not the greatest elements because they themselves are incomparable. So they are not greater than or equal to all of the others. So they are maximal, yes, but they are not greatest elements, H and I. So in this poset, we do not have a greatest element. We have maximal elements, but we do not have greatest elements. For subsets, let's say A, B, C. So this is my subset. Clearly, the lower bound is A. It's also the greatest lower bound. And the upper bounds for this subset are, of course, E. It's not D because D is not related to C. We also have F. Again, G is not related to C. We also have H and I. So the upper bounds are E, F, H, and I. And the least of these is E. So E is the least upper bound of the subset ABC. For the subset HI, the lower bounds are, remember what lower bounds are, the elements in set A, in the poset, that are less than all the elements in the subset. So we have F, not G, because G is incomparable to I. We have F and all the ones less than F, these A, B, C, D, E elements. Okay, so A, B, C, D, E, F are lower bounds of subset H and I, and F clearly is the greatest lower bound. What about upper bounds? For H and I, we do not have any upper bounds because there are no elements in the entire poset that are greater than both H and I. The two of them are incomparable, so none of them are also upper bounds. Finally, let's look at the subset A, C, D, F. So this is A, C, D, and F. This subset here. Okay, B and E are excluded here. And since A is in this subset, it's obviously a lower bound. And it's also the greatest lower bound because it's just by itself. And what about upper bounds? F itself is an upper bound. Now this time it's inside the subset, but also H and I are other upper bounds, but the least of them is F. So F is the least upper bound of this subset. Okay, so back to lattices. Now we described posets and we made the definitions maximal, minimal, greatest element, least element, and upper bound, lower bounds concepts in a poset. And now coming back to the lattices, we can actually define a lattice as a poset which has a certain property. Okay, a poset in which every pair of elements has a greatest lower bound and a least upper bound is a lattice. Okay, so we can show that this definition is equivalent to the definition we have seen earlier, but we are not going to do that. Essentially, if you have a partial order and every pair of elements has a greatest lower bound and every pair of elements has a least upper bound, then we can say that this structure is a lattice. For instance, the set of positive integers along with the relation divides is a lattice. Or the set 1, 2, 4, 8, 16 along with the relation divides is also a lattice. In fact, this is a total order because 1 divides 2 and divides all the others. So 2 divides everything except for 1. 1, 2, 4. So 8 here and 16. This is the Hasse diagram of this poset. It's clearly a lattice because it's a total order. it always has upper and lower bounds. And the power set of a set, along with the relation subset, again, is a lattice. And here you see some Hasse diagrams that are lattices. This one is a lattice. You take this one, these two, or these two, or these two, for instance. The least upper bound for these two is this one, and the greatest lower bound is this one, for instance, because it doesn't have to be inside the subset. Or this, when you take, for instance, this one and this one as the pair, this is the least upper bound, greatest lower bound, and this one is the least upper bound. Or if you take this one and this one, the same goes. Or you take this one and this one actually is the greatest lower bound, and this one is the least upper bound, and so on. So you pick any pair, you can find a GLB and an LUB, which means this is a lattice. For instance, 1, 2, 3, 4, 5 with the relation divides is not a lattice. For instance, because if you draw the Hasse diagram, 1 is at the bottom, and you have 2 here, 3 here. 2 and 3 are incomparable. 2 is related to 4, and well, you also have 5, like so. For instance, if you take 3 and 4, you have a greatest lower bound, which is 1, but you do not have a least upper bound. You do not have an upper bound for these two. Therefore, this is not a lattice. Or this one, take this one for instance, the Hasse diagram given here. It's not a lattice. Why? Because BC has no least upper bound. Why is that? Because the upper bounds for BC, look closely, is D, E, and F. D, E, and F are upper bounds for the subset BC. However, you do not have a least upper bound because D and E are incomparable, and F clearly is not that because D is less than F. E is also less than F, but D and E are incomparable, so I cannot say this is the least upper bound. Neither D nor E is a least upper bound, so this structure is not a lattice. And on a lattice, we can define the operations meet and join. If S is a subset of the poset, join of, well, this should be S, the subset. Okay, join of the subset S is the least upper bound of S, and meet of the subset S is the greatest lower bound of the subset S. Okay, every subset and of course every pair has meet and join on a lattice by definition, because that was the very definition of a lattice. Pick every pair, you have a GLB, you have an LUB. That was the definition. So obviously we can define meet and join as binary operations also. So here you see the general structure of meet and join on a lattice. You have A and B. Of course, if they are comparable, either way, then one of them is the meet, the other is the join. Okay, you can also have some stuff in between, like so. A here, B here, some other element C in between. But this also means, due to transitivity, A is related to B. A is less than or equal to B. So A here is going to be the meet, and B is going to be the join if they are comparable. If they are not, then this is the picture you have. If they are not comparable, then you have some other element that is the meet and the join. And these operations have the following properties. First of all, the result of these operations are unique. And obviously these are in the set, so it's closed. And the operations are idempotent. So A join with itself is itself, and A meet with itself is itself. The operations are commutative. The order doesn't matter. And the operation is associative. Both meet and join are associative. So these are valid, okay? Now, based on these, we have the notion of a complemented lattice. On a bounded lattice with the least element or the bottom element 0 and the greatest or top element 1, an element x bar is called a complement element of element x if this is satisfied. First one, x joined with its complement is equal to the top element, and x meet with its complement is, sorry, this should be the bottom element. Okay, so this is the definition of the complement operation. And be careful, it says in the definition a complement of element x. So it doesn't say the complement. So from this, you should understand that complements may not be unique. Here's an example. Well, of course, a lattice in which every element has a complement is called a complemented lattice. But in this example, you see, well, this is a complemented lattice because every element has a complement. 0 and 1 are complements of each other. That is clear. And C has the complement B. Okay, so their greatest lower bound is 0, and their least upper bound is 1. And A and B, the complement of A is B, because, well, the complement of A cannot be C, but it is B, because, again, when you meet them, it's 0. When you join them, it's 1. But you see, element B has two complements. C is a complement of B, because the definition is satisfied, but A is also a complement of B. So you see, B now has multiple complements. So this is also possible. But this here is a complemented lattice because all elements have a complement. It can be multiple, but you have at least one for each. And then we have the concept of a distributive lattice. A distributive lattice has the distributive rules satisfied. Okay, so the join operation distributes over meet. Also, the meet operation distributes on join. So it goes both ways. You have to be careful about this. With the structures we have seen so far in the field, in the ring, in the vector space, etc., we just had distribution of multiplication over addition. Now here in lattices, it goes both ways. Okay, meet distributes over join, and join also distributes over meet. Now, when you have distribution and complements together, okay, what we have is now a Boolean algebra. Okay, a distributive lattice has this property. Every element of a distributive lattice has at most one complement. So this means 0 or 1. It doesn't have to have one, but when it has, it doesn't have more than one. And when you also have a complemented lattice, you guarantee that all elements have at least one. When you combine them together, this means every element has exactly one complement. So a complemented distributed lattice is what we call a Boolean algebra. And again, since you see a here and not a the, you should understand that there is not a unique Boolean algebra, and Boolean algebra itself is an algebraic structure where you can define different multiple Boolean algebras.